Welcome back to Applied Mathematics. In this video, I wanted to talk about the equations of lines. We've seen previously that an equation in two variables, which can be written in a form like ax plus by equals c, is first of all something that we call a linear equation. It's called linear because it has the variable x, which is kind of by itself. It has the variable y, which is kind of by itself. They're not being raised to powers, they don't have other operations being done to them, and that is the characteristic that makes something called linear. We've dealt with linear equations in one variable, and we're able to solve for that particular variable. This is a case of a linear equation in two variables. It's not the only choice that you have as a tool for writing a linear equation in two variables. If I get my head out of the way, we can start looking at a couple of others. This form of an equation is sometimes called the standard form. Or I've seen it called the general form, depending on which textbook you are looking at. This is the one that mathematicians turn to first when they are trying to describe the equation of a line, but it's really not that helpful. First of all, there's no real way of getting a single equation out of this. For example, if I had something like 3x plus 2y equals 12, and I multiplied both sides of this equation by 2, I would have 6x plus 4y equals 24. And if I divided that equation on both sides by 5, I would have 6/5 x plus 4/5 y equals 24 over 5. All of these are perfectly valid ways of writing the exact same equation in standard form. So, standard form, terrible. We don't like it. We choose not to use it when we can avoid it. Perhaps the most common form is if you take this equation and you solve for y. Because you have that rule of solve for y, you get y by itself, there's only one way to write an equation in this form, which makes it a lot nicer. Describing its function, this is often referred to as slope-intercept form. You'll also sometimes see this referred to as function form. We'll be talking more about functions in the near future, and you'll get to understand why that is such a name. All right, but the slope-intercept form, definitely the more common name for this thing. And the reason for that name is that the parameters in the equation give you the slope and the intercept. The slope of the line is always going to be m. The y-intercept of the line is always going to be the point 0, b. And then I've got one more version for you. If you go back to the standard form and you divide both sides of the equation by c, you'll end up with a different way of writing things out. Which I might be able to interpret as x over a plus y over b is equal to 1. I've seen a lot of names for this. My personal favorite is the intercepts form. I've also seen this sometimes referred to as the elliptic form. If you go onward to study ellipses at some point in the future, you'll understand why. But I'm getting a little bit ahead of myself. Just like with slope-intercept form, this intercepts form is nice because it is unique. The right-hand side of the equation must be 1. And the left-hand side of the equation must be x over some number plus y over some number. There's only one way you can get that to happen. And once you've done so, the b in this equation will be the same as the b in the slope-intercept form, and the a will also have a useful purpose. The x-intercept of the equation is the point a0. The y-intercept of the equation is the point 0b. And so when you have an equation in one of these two forms, you can graph it very readily. Let's jump into a nice example. X over 7 plus 3y over 5 is equal to 1. I want you to notice here that this is almost in the elliptic form, in the intercepts form, but not quite. Because we don't have y over some number, we have 3y over some number. But that's actually pretty easy to take care of. Divide top and bottom of that fraction by 3. And doing so will give us x over 7 plus y over 5/3 equals 1. This is not what we would consider a nice version of the equation because it has that complex fraction, a fraction that has a fraction in it, and that's problematic. But it does give us the information we need. We have x over some number, we have y over some number. Just by looking at that, we know that 7, 0 and 0, 5/3 are 2 points on this line. If you've not seen this form of an equation of a line before, if you've not come across this, I encourage you to double check that. Take those 2 points, plug them back in, either here or back at the original equation for even more fun, and simplify. Verify for yourself that the left-hand side simplifies down and becomes 1. So it is in fact a point on the line and we can graph it. These 2 points are relatively easy to find because they are axis intercepts. So I'll go ahead and sketch out some coordinate axes real quick. And as I've done before, I'm going to, since I don't have any context of what x or y mean, I'm going to err on the side of caution and use the same scale in both directions. The point 7, 0 is right there. 0, 5/3. This is one of the few places where an improper fraction is probably better than a mixed, this is one of the few places where a mixed number would probably be better than an improper fraction. So I can rewrite that point as 0, 1 and 2/3. Now I know that I'm going 2/3 of the way between 1 and 2, which is somewhere around about there. And doing my best to play connect the dots, I get that my equation of my line looks something like that. One more example, in this case y equals 5x over 3 minus 4. Very similar to the last one, this is almost but not quite in that standardized form, the slope-intercept form in this case. But resolving this one is even easier. Order of operations, playing around a little bit, 5 times x over 3 is the same thing as 5 over 3 times x. And just by doing that, we can play our matching game. We can see that the slope is 5/3, and the y-intercept is 0, -4. Let's try that again with the x-axis actually along one of the lines of my graph paper. There we go. All right, so I've plotted my point in question. Now, graphing using slope is a little bit weird if you're not accustomed to it, but once you get used to it, it happens so fast. Our slope is 5 over 3. And in general, we say that slope is rise over run. So I'm going to rise by 5. I'm going to run by 3. And in doing that, I arrive at this point, which will also be a point on my line. I'll do that one more time. Rise by 5, run by 3, and that's another point on the line. Playing around with properties of signed numbers, well, 5 over 3 is the same thing as -5 over -3, so I could also do this going in the other direction. I can rise by -5 and run by -3, and I come over here, which is going to be yet another point on that line. All I have to do is play connect the dots. Remember that my line extends beyond all of the dots that I have, and the red line there is the graph of this linear equation. All right, so there we have it, a couple of ways of looking at a linear equation you may or may not have come across in the past. It may have been a while. But hopefully that makes sense. Hopefully that gives you the tools that you need in order to sketch the graph of a linear equation without having to put too much effort into it. I think that's a good place to wrap up here. So as always, thank you for joining me, and I'll see you in the next video.